Log on, tune in, find out. Another good idea from Cambridge.
So, yes, thank you for the introduction, Dr. Tobias. Thank you very much for giving me the chance to present some ideas on optimal designs in nonlinear mixed effect models. Okay. Especially for the estimation of the population location parameter, as did Rainer before. So, short outline of my talk. At first, I will talk a little bit about the bottleneck in this experimental design problems, and this are the information approximations. So we don't have a closed form of our Fisher information which we want to maximize. So we need some approximations to this information matrix. And after giving some approximations, I will talk a bit about experimental designs in this model, and especially about the difference between the designs for the different approximations. So as Rainer had this before, we have some concentration time profiles for different individuals. Here we have 5 individuals, and it's the exponential decay model, and these functions are similar, and every individual has a known function, and this response function is defined by these individual parameter vectors, which were called in Rainer's talk BI. I will call them beta I, and they are assumed to be realizations of random variables. This allows to model all observations together in one common model, and this leads us to the mixed effects models, which is defined in the 2 stages. At first, we have the intra-individual variation. So we have a model for the ith individual, which is with a response function eta, and depending on this individual parameter vector beta I. And we have this unknown observation error, which is here assumed to be normally distributed. And the second stage is the inter-individual variation, where we assume that this individual parameter vector beta I consists of a population part, a fixed part. This is the mean beta, and we have some random individual effect, which is here denoted as BI. So a little bit, I use another notation than Rainer did, and these random individual effects are assumed to be normally distributed with a mean 0 and variance matrix sigma square D, and these sigma squares, these are the same, so it's just for some, without reasons really. So it's for, so, and as in the earlier talk, again, we assume that the individual random effects and the observation errors are independent. Yes, and the individual parameter vectors, they are for sure assumed to be all independent as well. And our aim is here the estimation of the location parameter vector beta, no prediction, just estimation of the location parameter. We assume that sigma square and sigma square D are known. If they are not known, these problems don't get easier, they get much worse. So let's start with some easy stuff. The vector of the individual observations for the ith individual can then summarize now with the vector valued response function eta, which depends on the design xi, which comprises the experimental settings xi1 to xi-mi, and this is then the observation error vector, and this will be in the following: the design matrix. Here is not necessarily a beta, there might be some other vector beta 0, some guess of beta, then we have to replace here this by the beta 0 or something like this. And yes, we want to optimally estimate beta, so we need some insight, some knowledge of the covariance matrix of beta hat. This isn't easy to get, and maybe when we know the statistical model, then we can compute a lower bound of the variance of any unbiased estimator by the inverse of the Fisher information, which unfortunately cannot be expressed in a closed form here, but we have this form as the product of the score functions and our here's our probability density for the observation vector yi is here then just written in integral form, because we have no closed form representation here. And this is here the normal density with mean eta of beta I, and here the normal density with mean beta I and variance sigma square d. Yes, for nonlinear response functions, this has no closed form representation. For linear response functions eta, this is just again a normal density. But in these pharmacokinetics, we unfortunately have usually nonlinear response functions. And so there are two approaches to solve this problem of the missing closed form representation. These are basically just linearizations of the model. So in the first, this would be a linearization in the unknown but true parameter vector, location parameter vector beta. Then we get a nonlinear normal model when we assume that all linearization errors are negligible. So we have here the mean of this observation vector then, and here we have something with expectation 0 and here expectation 0 as well. Both are normally distributed. So we have here the term inducing the variance, and note here that this variance matrix depends on the unknown parameter vector beta, so that we have this heteroscedasticity. And the second approach is the linearization of the model in some guess beta 0. This is the linearization which Reiner used as well. And there we have here a normal linear model, and here we get the variance matrix, which now depends on the guess beta 0 and not on the unknown parameter vector beta. This is nothing more than a linear mixed effects models again. Yes, the difference is when we take a look at the Fisher information. So for designing experiments, one usually assumes that both models, one of these models is now the true model, and we then compute the likelihood, take the derivative of the score function, and then we take the score function and the product and compute the Fisher information, and then we assume that this is the true Fisher information of the nonlinear mixed effects models here. This information matrix will then behave as in the linear mixed effect models, as was said by Reiner, but this will have some additional term such that this information is always bigger than the information in the linear mixed effect models. So one of these approximations isn't the right one. Probably both aren't the right ones. But at first, let us think of another alternative motivation. So why don't just at first calculate the score function and then take the expectation of this? We know there's no closed form solution, but maybe we can approximate there something. And the score function can be easily represented in this way if we assume interchangeability of differentiation and integration. And this yields then for the information matrix these representations in conditional moments. So the first readily follows from the product of the score functions, and the second is then a consequence of the equality that variance beta I is equal to the expectation of the variance plus the variance of the expectation of beta I. So maybe we can get a bit more insight if we approximate instead of the model, instead of this, approximate just these conditional moments. For sure, one might approximate these moments just by using some Monte Carlo methods, but we want to have some insight in the influence of the experimental settings on the information matrix, so we need some other methods. And one method might be then to apply some Laplace approximations. It was Tierney and Cadane who had some ideas on accurate approximation of posterior moments using the Laplace approximation. Here we have some weighted sum of squares. This is the original density, and we want to approximate this in the middle by some normal density, and therefore we use a second order Taylor expansion around the vector beta I hat, which minimizes this sum of squares, which is here in here. And then we get something an integral what has a closed form. Unfortunately, this beta I hat depends nonlinearly on yi, so that this doesn't yield any new insight. But no, not but one might as well take a look at some other linearization, and this would then be if we just linearize not the whole if we don't take the tail expansion of the whole function h, which is this sum of this is the sum of squares, but we might just take some linearization of this eta. This leads to similar results, but with another variance matrix. And one might then use the same approximation for the numerator of the conditional density. And what we then obtain is that the conditional density of beta I given some observation yi can be approximated by some normal distribution. I don't claim in any way that this is normally distributed. This isn't normally distributed, but we just can approximate it by some normal distribution. And with mean beta I hat, this is the beta I which minimizes this sum of squares, and this covariance matrix. Unfortunately, as we had it before, both depend on the observation yi. Both depend on yi nonlinearly, so that we cannot compute the moments straightforwardly without yet another approximation. However, if we take, instead of this beta I hat minimizing the weighted sum of squares, this true location parameter vector beta, then we come to this approximation of the conditional density here. And here we have, this is the only point where the observation yi influences this conditional approximation of the conditional distribution. Here we have no influence of yi at all. So this leads us straightforwardly to two approximations of the Fisher information. The first by approximating by the conditional expectation here, and the second by the conditional variance. And especially the second one is an approximation of the information which is well known. It's the same as doing a linearization in a guess beta 0. So it's just a linear mixed effect models information what we get here. So Rainer mentioned already that there are other possibilities to approximate the information, or other information matrices which might be used. One is the quasi-likelihood information when we know the moments. So if we don't know if we cannot compute the expectation or the variance in a closed form of the unknown parameter vector beta, then this doesn't make much sense. And the second, the fourth information approximation here is the one given by the nonlinear heteroscedastic normal model, as on the fourth slide, I think it was, where I said that this might be a case occurring as well. So here you see we have this information as in linear mixed effect models, or in this approximation by the Laplace idea, and we have here this additional term which is somehow depending on the heteroscedasticities. Now we come to a little example, and this is not the exact example as Rainer had it. We have the exponential decay as well, but as the concentration cannot be negative, we assume that our observation errors, that they were proportional and log normally distributed. So what we did was we just log transformed the whole model. So what we observe is the log concentration here, and our individual parameters are assumed to be proportional and log normally distributed as well, and we transformed them too. So we get to this model equation, which is nice because it has a closed form representation for the mean and for the variance, so we can compute there the quasi-likelihood information as well. So for this model we did some simulations, and here you see the dependence of the components of different information matrices on the time point chosen, and these scatter plot in there, the black points, circles, they are the observed values in the simulation for the Fisher information. And here you see especially here you see really well the additional information given by the information of a nonlinear heteroskedastic model, and you see as well that the approximation by linear mixed effect models is here rather good. It's not perfect, but it's really good. So here you see, for example, that there is a difference, but no big difference. For designing the experiment, one might already see here that probably the optimal designs here won't differ much, as the components of the information matrix depend, as the dependence of the components of the information matrix on the time is similar for all different approximations of the information matrices. So now we come to the next point, the experimental designs. As the model itself is built up in two stages, the experimental design is as well. So we have at first the individual experimental designs, XCI, which describes the experimental settings for an individual, and the second stage are the population designs. These are the proportions of the individual designs in the whole population. So if we now assume that all populations are observed with the same number of with the same number of times, then we have that the population designs are nothing more than approximate design on the design space, on the m-dimensional design space X here. So what we want now is we want to minimize the covariance, which is approximately the Fisher inverse of the Fisher information, or we want to maximize the Fisher information. Different criteria are written down here. There are a lot of others, and I won't go into detail. How to do this? We might analytically use the equivalence theorems to optimize the designs, or we take use of some algorithms, which are mainly based on the equivalence theorems as well. So here the equivalence theorem for linear optimality, for d-optimality is the same thing, just with the L is here then equal to the inverse of the population information, which is here nothing more than the sum over the individual information matrices, as the observations of different individuals are independent. So if this is the sensitivity function, if this is smaller than 0 for all individual designs C, then the design theta star is optimal. In our model with this exponential decay, and when we assume that we have just one observation per individual, a very sparse design, then one can easily construct the optimal design analytically. Here the d-optimal design is given by all sets of point x1, x2, all pairs of points x1, x2 in this interval fulfilling this equation. So especially if there are no such points in the interval, then the optimal design is to observe at the beginning of the time interval and at the end. This is rather quickly seen. The first one has here the experimental settings. They enter the model just linearly, and so the sensitivity function, here the modified sensitivity function, is nothing more than a quadratic polynomial. So quadratic polynomial which should be smaller or equal 0. A quadratic polynomial has at maximum one maximum or one minimum. So there can be just 2 design points, or the sensitivity function is equal to 0 on the entire design space. That's the other possibility. So for our example, this leads us to the following designs. Note that the second design and the third design, also for the design for the information matrix in the linear mixed effect models, this is not unique, and for the quasi-information, this design is not unique as well. But for the information matrix based on the variance of the expectation, and for the nonlinear heteroscedastic model, these are unique optimal designs. We computed them with a quasi-Newton algorithm and with penalty functions. So some other kind of optimization algorithm. And if anyone is interested in this numerical algorithms, I would like to discuss them. And yes, another time. So here is the efficiency, and as you see, all designs are rather efficient. So there's a question whether there is some big impact in choosing different information matrices, or whether there is no big impact. And unfortunately, when taken another one compartment model, this time with first order absorption, one sees rather quickly that there is a big difference. Here in this model, we can't compute the variance and expectation in a closed form. So we just have here the information based on the linear mixed effect models and on the nonlinear heteroscedastic model. Here you see the sensitivity functions, and these are local optimal designs. They depend on the parameters and the variance and the design region for sure. Yes, and here you see that the designs differ much, and not only designs, but the efficiency as well. So here we have the efficiency of the design zeta 2, which is optimal for the linear mixed effect models information, in terms now of the nonlinear heteroscedastic information, and it's just 55%. And otherwise, the efficiency of the design zeta 4 in terms of the design zeta 2 is just 66%. So it matters which approximation one uses, and so there's still much work to do. And what we got now is another motivation of the information matrix for linear mixed effect model, for nonlinear mixed effect models by a linear mixed effect model, and we saw what is obvious, that different information matrices yield different designs. But what is more interesting, even that these designs might be really not efficient in other approximations. And for future work, I would like to think once more about that what Rainer already told, whether this information matrix of the approximation by linear mixed effect models is really, whether this is realistic, whether there is some estimator which has this asymptotic variance matrix. And another thing which one might think about is whether the Laplace approximation in the true individual parameter vector beta I, which results this will yield. And the third thing is the efficiency of optimization algorithms, whether the standard Fedorov or the Win algorithm always outperform a quasi-Newton algorithm or not. I don't know, and I would like to discuss about this on this workshop with some people if there are any people interested. So thank you very much for your attention, and
now it's time for discussion. If you have questions, ask them.
So you've assumed that the variance of the random coefficients is known all along the talk.
yes.
So in your calculations, did you look at small variances or also large variances and looked at the difference in your results?
In these calculations here for the optimal designs here, these are all just locally for an example.
Yeah, but you had to assume a number for a value.
Yes, I assumed a number of values.
Yeah, so was it relatively Small or relatively large? Or did you look at various?
It was bigger, much bigger than the variance of the observation errors. So it was 10 times at least the variance observation of the
Because this may
observation.
affect your result.
Yes, there is a here is no effect. This is a general result. It's just so here you should plug in then this variance matrix if you take the linear mixed effect models approximation, or if you take the quasi-likelihood information, then you should take the true variance matrix. And this then depends on the inter-individual variance matrix here, and it's a global result, then. A global local result.
Any other questions? You rely on a sequence of approximations, which make it possible to analyze
Yes.
relative ease, let's say. But have you tested the quality of those approximations by comparing the results with the Monte Carlo approach, for example?
Yes, we did this just in this one example yet, because, for example, for the one compartment model with the first order absorption, there it was this at the end. Okay, don't switch to this now. There we have the problem that the parameters are still fixed to some. They aren't allowed to get lower than some level, and so the normal assumption isn't met. So far we just did this Monte Carlo study here. Yes.
Okay.
So one thing of this Laplace approximation, which was stated by Tierney and Kidane, is that the good thing is that here the errors of the linearization, which one does in the exponent, that this cancels to some degree, so that this is more accurate than other approximations. And how far this holds for small individual sample sizes is not really clear, because, and the more it's not clear for how far this holds for the approximation just in the population parameter vector beta. So there is still some work to be done. Yes?
Yes.
Like in the previous talk, Rainer mentioned that one should investigate the asymptotic properties of the estimator. And this is difficult also in the case where the matrix is known.
Yes.
Case here.
In this case, it's typical as well, yeah. So there are some publications which say yes, everything is consistent when we take generalized linear square estimation or Lindström-Bates estimators for nonlinear mixed effect models, but in fact there are other publications which say that which make some examples to show that not everything is as it should be. So I think there will be a lot of discussions on these topics in August when there is a workshop on generalized nonlinear mixed models.
So we'll support Tobias once again.